Okay, great. So my name is Bo. I'm from Vision Euler. So Vision Euler is a provider of software codecs and also end-to-end cloud-based video streaming solutions. So today I'm going to talk about how to scale up video encoding pipelines by improving the per CPU encoding efficiency. Okay. So the outline of my talk, so I will first briefly introduce the background and also the problem that we have solved. And then I will propose our per CPU encoding efficiency optimization technology. And then I will talk about how we implemented this technology using in a fast and efficient way. And then I'll present some performance results comparing our encoding technology with the open source X264 and 265 encoders. So, as well known, video encoding is a computation-intensive task. It is very challenging and costly to scale up video on demand and live encoding workflow in the cloud. And the VOD encoders needs to run faster to reduce the turnaround time and also improve the throughput of the encoding systems. And live encoders needs to run more efficiently to allow more concurrent jobs, live jobs, per server. So these are all required by the streaming services nowadays. So to achieve these goals, we propose the per CPU efficiency optimization technology called PCO by improving the per CPU encoding efficiency. So specifically, we simplified our encoder's internal processing pipeline, and we also developed AI and machine learning-based intelligent video core encoding algorithms, and we also highly optimized our encoder software. And we believe that to achieve higher encoding efficiency, we must not give up bitrate saving and visual quality. And also, we want to make sure that our encoder run faster, software encoder can run faster while maintaining the same level of low CPU utilization and also energy consumption for the end devices. And how can we improve the per CPU encoding efficiency? So this is the workflow of our encoder pipelines. So we do a lot of intelligent pre-analysis and pre-processing. So from left to right, we have the video source coming into our systems, either professionally generated content or user-generated content. And we have a scene categorization module that identifies the type of the video source. Can be premium content, video conferencing, screen sharing, online gaming, animation, outdoor events, or sports. So for different video sources, we apply different encoding recipes to it. And then we do a lot of pre-processing to the video, including sharpening, frame rate conversion, denoising, deblocking, HDR to HDR enhancement, color space conversion. And I want to highlight our region of interest detection that can rapidly detect human faces, texts, and numbers within the picture in an efficient way. And after the pre-processing, we apply a lot of machine learning-based processing to the video, which include adaptively control the bitrate and also the machine learning-based optimization, lots of optimizations, and content-aware encoding, as well as per title encoding. So this is the workflow of our per title encoding engine. The source video comes into the pipeline, and we run some pre-encodings on the video source using the fast preset, so it takes less time. And then we calculate the VMAF score of the pre-encode, and then we extract the spatial and temporal features from the source video using machine learning technology. And we then derive the optimal encoding ladder for this specific title. and also derive the encoding parameters, including the CRF value, the resolution, the bitrate, frame rate. The idea is just to skip certain encodings which could result in the same level of quality, which are redundant. So we also detect the region of interest for each picture that comes into our encoder. So we detect the human faces, text, and number. So then we allocate more bits to these ROI regions and the most perceptually significant areas, such that we can achieve better quality while still maintain low bitrate. So this example, two pictures give an example of how important ROI detection is for our encoders. So on the left-hand side is the picture generated by open source X265, and right-hand side is generated by our encoding technology. As can be seen, our picture has a much more clear human faces, text, and number than open source generated content. And this gives us much higher VMAF scores than the open source one, about 9 to 10 points higher. At the same time, the video bitrate is still the same for these two pictures. And we also apply a lot of machine learning-based video core encoding algorithms to our encoder, including the fast reference frame decisioning. We basically choose the number of reference frames that are needed, and also the set of reference frames that are used for prediction, and also based on machine learning. And we also have fast and adaptive motion search, which include adaptively select the motion search method, the search range, and also search precision. And we also have fast merge and skip mode decisioning. And for intra-picture prediction, we use a machine learning-based intra-mode selection, which rapidly select the right mode from all 35 intra-prediction modes for H.265. And we also use different levels of intra-rate distortion cost calculation, including full picture calculation, Luma-only calculation while ignoring the chroma samples, and also local calculation and simplified calculation. We also have fast prediction unit partitioning mode selection, PU, and also fast transform unit size and type selection, TU. And next slide is about our algorithm for early terminating from the block partitioning process. So block partitioning is one of the most time-consuming operation in video compression. So we want to early terminate from the process so that we can save the codec complexity and save encoding time. And this is done by inferring the quad tree level of each coding unit based on the convergence pattern of RD cost at different levels, as well as the block partitioning information of adjacent frames. And based on that, starting from that inferred level, we then adaptively decide to move either upward or downward for further partition. And this is the workflow of the early termination algorithm. So before we traversing the quad tree recursively, we set a current level to 0. And then we also invert the level of the current block. And then we compare this current level with the inferred level and decide to either go bottom up or top down. So if we decide to go bottom up, we will first recursively partition the child blocks before, and also making partitioning decision for these child blocks before we go back to the parent blocks. And if we decide to go in a top-down manner, and then we will first make partitioning decision for the parent block before we go deeper into the quad tree partitioning. And how did we implement the software encoders in a fast and efficient manner. That's the next topic. So we applied a lot of optimizations to our encoder software, including combined use of coupled and decoupled software design pattern. So for those high complexity tasks, we combine all the complex logic in a single module such that we can avoid unnecessary inter-thread communication, as well as unnecessary data copying, memory copying. And for those less complex tasks, we want to split the tasks into multiple modules, a decoupled design pattern, so that we can maximize the code reuse and the flexibility. We also made a lot of optimization to our task scheduling algorithms to make the encoder running faster. We use intelligent caching to maximize data reuse and also cache hit ratio. And we also applied a lot of low-level customized optimization for different CPU architecture and instruction sets, including SSE and AVX2 for x86 and Neon for ARM architecture. And then we have many low-level C library optimization that are used to implement the video codec. And we also have thread pool optimization for improving the encoder's parallelism. Next is the performance result. So we compare our PCO 265 with the open source X265 in terms of the encoding speed. So we used two video sources from JCT-VC, which is the working group behind the standardization of H.265. And the video sources are 1080p, 60 FPS, and we use two CRF values, 27 and 32, and we use 4 threads to encode the video, source videos. And we choose a speed setting of very slow, and we encode the video on a server running AMD 12-core processors. And let's look at the table. So first, when the CRF value is 27, the top two rows, 27. So X265 was only able to encode the video at a frame rate of 4 frames per second. But our PCO 265 was able to encode at close to 17 frames per second. So this represents more than 300% speed gain over X265. And at the same time, the bit rate for us is only 1.4 megabits per second, while for X265 it's 1.8. So this is a 22% bit rate saving. So in terms of the video quality of the output video, both video encoders achieve the same PSNR, SSIM, and VMAP scores. And in terms of CPU utilization, our PCO 265 is only slightly higher than the X265, which means that we achieve a higher encoding speed without increasing the CPU utilization. And next is the result for CRF value 32, the bottom two. Again, X265 only encode at 5 frames per second, while our PCO 265 encode at 21 frames per second. And this is again close to 300% speed gain. And bit rate, we achieved a 10% saving compared to X265. VMAP score and CPU utilization are about the same for the two encoders. And next slide is the encoding speed, the result of encoding speed when different number of CPU cores were used for encoding. So this is slightly different from the previous slides where we only have 2 jobs. Well, this one is based on a large number of transcoding jobs and a large number of video sources. And we take the 50th percentile, the median frame per second value from all the jobs. So on the left-hand side is the result for 264, right-hand side is 265. As we can see, when there are 4 cores, 8 cores, or 12 cores, the X264, our PCO264 was able to achieve about 50% speed gain than the X264. The blue bar is X264. The green bar is the PCO264. So it's about 50% more, higher speed. Well, if we look at the 265 result, we are about 1 to 2 times faster than the X265. And this means that if we can increase the encoding speed, we only need fewer CPU cores for completing the same set of tasks. And this means cost saving, a lot of cost saving. Or we can, equivalently, we can use the speed gain to run the job faster, increase the job turnaround time, and improve the throughput of the transcoding system. So either way is good for the streaming services. And the last result is about the parallel encoding, the encoding density, how many concurrent live and VOD job we can run on the same server. So in this experiment, we run 4 and 6 jobs concurrently on the same server, and that server it has an AMD processor with 24 cores and 48 virtual threads. And input video is a 4K 422 60 FPS video, and the output target bitrate is 30 megabits per second. And we configured the encoder to read the frames, video frames, at the native speed of the source file. Let's look at the result. So on the top table, when there are 4 concurrent encoding jobs, and for both encoders we choose the speed setting of ultra fast, and X265 was only able to encode at 55.4 frames per second, which is lower than the native speed of the source, 60 FPS. So this means that X265 failed to achieve real-time encoding on the same server, even for 4 concurrent jobs. However, our PCO265 was able to encode close to 60 frames per second. So it's basically 60 FPS. So we succeeded in real-time encoding. And then let's look at the 6 concurrent jobs. X265 was only able to encode at 43 frames per second, while the PCO 265 was again able to achieve real-time encoding at close to 60 frames per second. So this means that our encoder can allow more concurrent live or VOD jobs per server, and this can save a lot of computing cost for the services. And yeah, so we only need fewer servers and fewer CPU cores to run the same thing. Okay, so let's come to the conclusion. So we noticed that improving encoder efficiency can save huge for the streaming services or any companies that use video streaming, video encoding on the cloud computing cost. And by increasing the encoding speed, it can reduce the job turnaround time or improve the encoding system throughput. So one benefit is saving, the other benefit is higher throughput. And we have shown that our PCO technology optimized the per CPU efficiency to make the video encoding faster, more cost-effective, and more scalable. And we believe that by reducing the computing cost and also improve the system throughput, we can achieve a higher customer retention rate. That's the ultimate goal for us. Yeah, so that's the end of my talk. Any questions?
Yeah, can you go through it one more time for the people that weren't in the room?
Okay. Yeah, maybe next time. Yeah.
I've got two questions. Have you done any tests on Intel platforms? Because all the results are from AMD platforms. Is it similar or?
Yes.
Repeat the question too.
Oh yeah. Okay. So the question is, have we run any Intel any test on Intel processors? Since all our my result is on AMD or ARM. So the answer is that we also have results for Intel, but I'm only presenting the result for AMD here.
Are they similar results?
Yeah, I think so. But for ARM, it's different. Yeah. Yes.
Second question I have is, how well does this work in a virtualized environment?
Okay, for virtualized environment. I'm not sure. I think our tests are running on bare metal and as well as virtualized environments. Our systems is employed in Docker containers. Yeah. Yeah. Okay, great. Thank you.